we're now on to the next part of our program, and we'll be hearing from the first of our student presentations. So this week you'll hear a range of student presentations over the next few days. As you know, each of you has a short period of time to be able to talk about the project that you've been undertaking while you're here. And there will be time allocated at the end of each session for all of us to ask questions. Just a reminder for those who are speaking up here and also people who will be asking questions, speak into the microphones and then also the roving mics for those asking questions, because we are recording this and live streaming it. So for this, I'll hand you over to Jodie.
I will be looking after the next session today. My name is Jodie Costa and I'm part of the Talent Management and Coordination team. Student presentations will go for 3 minutes for those presenting individually, and for those presenting as part of a group, the presentation will go for 5 minutes. We will give you a warning bell when there's 1 minute remaining and 3 bells at the end. Our student presentations will begin with presentations from Aerospace Division. Aerospace Division provides support and innovative solutions to enhance the operational capability, survivability and availability and safety of the Australian Defence Forces aircraft platforms and reduce the costs of owning them. Please welcome our first presenter, Daryn Benecke.
Good morning, my name is Daryn Benecke and I'm an undergraduate student at Swinburne University studying robotics and mechatronics. While at DST, I've been studying fibre optic sensors for defence platforms. The reason we're studying this work is we can't always attach conventional strain sensors onto devices, as sometimes they'll disrupt the fundamental function of that device, such as a propeller. The reason we study fibre optic sensors is they can overcome certain limitations of conventional electrical strain sensors, such as conventional strain sensors are sensitive to electrical interference. They are heavy once installed because they have 3 wires that need to connect to the testing equipment, and that needs to be supported by a gantry, and they're very time consuming to install. Fibre optic sensors, on the other hand, are immune to electrical interference. They are lightweight, and when we install them, they're convenient to install, and as you can see in the left-hand image, is barely visible, and that fibre optic there is 5 metres with over 7,000 strain sensors. While at DST, my work is broken into roughly 4 areas. Initially, I was investigating 3 different fibre optic strain sensing technologies that are embedded into coupons, which are presented at a conference beginning of April. We then investigated the difference between surface-mounted sensors and embedded sensors. We put those coupons aside and moved on to investigating a set of coupons where we could characterize the inhomogeneities of composite materials and also barely visible impact damage. This work was presented at a conference late last year. Near the end of my placement, I was fortunate enough to be involved in a structural test of a PC-9 wing, where the wing was actually tested to failure. And with that wing, we placed a 5 metre optical fibre under the wing with 7,000 strain points. What was most interesting about this area of work was that we were actually able to detect the beginnings of failure of that structure almost a full hour prior to it failing, which holds great promise for structural health monitoring purposes. My vision for this work is to one day be able to embed this technology in an air platform and give that platform a nervous system. You'll then be able to sense the flight loads that it's experiencing and or damage, and enabling new forms of flight control systems. Thank you very much for listening.
Thank you, Daryn. I'd now like to welcome Jeremy Kieruj.
Good morning, my name is Jeremy Kieruj. I'm an undergraduate student studying at Swinburne University Technology. And for the past 12 months, I've been part of the IEP program with Advanced Diagnostic Systems Group at Fisherman Bend. The main area of focus of my project has been using thermoelastic stress analysis to localize the tip of a fatigue crack. So that the sort of in a nutshell, thermoelastic stress analysis is the process of using an infrared camera to image a surface or a specimen of which we can detect temperature variations due to stress changes when that specimen is undergoing dynamic loading. This technology has many capabilities many applications, The main application that I've been looking at is material characterization, especially in terms of determining the fatigue resistance of materials. It can also be used as in-flight monitoring of structures, and also the design and prototyping phases of aircraft as well as structures. I know Lockheed Martin have used this system in the final stages of their F-35 or JSF development, which is now in service with the RAF. The current technology available, the most accurate current technology available, is basically optical microscopes, whether they be digital or digital analog. However, they do suffer from a variety of issues, such as it's quite difficult to actually identify what the crack tip or where the crack tip is itself due to lighting, surface imperfections, crack closure. So this requires a skilled technician who essentially has to sit through the entire testing phase and accurately monitor where the crack tip itself is. Again, this is subjective to the technician's skill. So there is a lot of, there is quite an issue with human factors there. Whereas TSA itself, which has been developed or being worked on at DST for the past decade or so, in conjunction with software that's been developed by DST, Mighty, is able to remove this human errors, as well as provide a fully automated capability of tracking fatigue cracks themselves through thermoelastic stress analysis. However, there is an issue with blurring of these images, as you can see here, and this is due to the rate at which the specimen is tested. So this is where my work comes in. I've been able to develop, in conjunction with mathematical modelling, model based on experimental results. We've been able to remove this blurring, which is caused from heat diffusion. So essentially, we've been able to remove the effects of frequency, creating a much more accurate model. So in the future, I hope to have my research implemented into the Mighty capability and allow for a much more accurate analysis of fatigue cracking in the future. Thank you for listening.
Thank you, Jeremy. Please welcome Henry Kissick.
Good morning, everyone. My name is Henry Kissick. I'm an undergraduate student at Swinburne University of Technology, and the last 12 months I've been at DST on the internship program. In the last 12 months I've been looking at directing acoustic energy with relaxer ferroelectrics. Relaxer ferroelectrics are essentially piezoelectric crystals that have directionality and high efficiencies associated with them. They have application in medical ultrasound, and what we are using them for is essentially medical ultrasound, but not for humans, but looking at aerospace structures. So the concept is traditionally to use traditional piezoelectrics, and take an inch-by-inch approach, inspecting entire structure bit by bit, which is extremely time-consuming. And this is due to the fact that these crystals can only send a pulse in any one direction equally. The difference with the relaxer ferroelectrics, as I mentioned, the directionality, is seen in the upper right-hand image and also in the lower left-hand corner in this clover shape. Shows that what happens is when you put a voltage in the crystal, at any given angle, you'll receive a different force output, a different displacement output. And the concept is essentially using these relaxer ferroelectrics embedded into a structure, using triangulation, and as an excitation goes into a structure, we can use the signatures given by the relaxer ferroelectric elements to pinpoint the location of the damage and in the future perhaps even the type of structural irregularity which is happening at that point. So what did I do at my time in DST was I spent a lot of time characterising and profiling these relaxer ferroelectric single crystals and trying to find the material properties which define this behaviour. And also a big struggle was the fact that directionality was unknown, so these crystals were unmarked and we had to profile each individual crystal. And this was a process which 1 year ago we had to take the crystals to the synchrotron and perform X-ray crystallography, which is extremely time consuming and expensive. We got that down to a 30-minute laboratory experiment. Also developed computer simulations to study the crystal's behaviour in free space and when attached to structures such as a thin plate, and also developed equations to analytically model this to reduce the time needed with computer simulations and iterate through results quite quickly. These results have also been published in an applied physics letter in DST Hums and presented at the CAMS conference in Wollongong late last year. Thank you for listening.
Thank you, Henry. Please welcome Brandon Lay.
Okay, apparently I have one slide. I'm going to present using that one slide. So I'm not sure what happened to the actual presentation. Apparently it wasn't uploaded. My work was to do with the metal 3D printing process and the thermomechanical simulation behind it. So what you have with the 3D printing process, as Graham Schaffer said before, it was it's a multi-physics and a multi-scale process. You have the powder scale, which is on the order of micrometers, and you have the individual scan vectors aggregate into the millimeter part or meter part. And so my 12 months here have been to investigate how you can simulate it and how you can apply it. So my group, the CMSM group, the Computational Materials and Structural Mechanics group, is interested in using residual stresses to predict fatigue, life, and potential crack locations that can occur. And within the additive manufacturing process, the metal 3D printing process, you have residual stresses develop non-uniformly because of the high temperatures that the process undergoes. And apparently I can't show any results because my presentation wasn't uploaded. Thank you for listening.
Thank you, Brandon. Please welcome Indo Leane.
So the question on everyone's mind for the next 3 days will be, what did this guy do at the DST? Well, my name's Indo Leane and I undertook an IEP position within the Aerospace division for 2018. Over the course of last year, I had a well-rounded experience where I developed my professional skills in all areas through undertaking projects that range from the supportive technical side of work to the novel research and development tasks. These projects revolved around the development of UAVs and looking at the methods for autonomous visual navigation that we can employ into these agents to allow for successful operation in dynamic environments. Such environments actively contest with the agent's ability to navigate, like in the case of a GPS-denied area. The group I worked with in Aerospace Division primarily uses the fixed-wing UAV pictured here. So after becoming familiar with the base UAV systems, I developed a VTOL UAV. I designed mounts for the new and existing components. I made a schematic of the avionics layout, and I used rapid prototyping processes like 3D printing and modeling to assemble a prototype, pictured here. The build was successfully tested and can operate with a 2 kilogram payload while boasting the vertical liftoff and takeoff capabilities, which eliminates the need for a runway like traditionally needed for a fixed-wing UAV, which allows this platform to take off in restricted spaces, so it can take off in a much smaller area. Then for the latter part of the year, I focused on a research task investigating the methods for autonomous visual navigation. I formed a research question to determine how viable is the power spectral density algorithm as a possible over-water means for navigation. So I formed a research question. The PSD method is an algorithm which decomposes an image into the sine and cosine components and uses the power spectral magnitude to estimate an angle of the waves. And this work is leading to an enhanced over-water visual navigation capability. So in the previous slide, the results are quite accurate in simulation. However, in the real-world test, the estimations would vary significantly. So I formed a hypothesis about the model that the algorithm uses, constructed experiments to test this understanding, and did this to determine the situations where the algorithm may be unsuitable. I did this by finding a suitable simulation environment to perform rigorous experiments, such as examples seen here. So from a Beaufort scale 1 to 4, midday to no sunlight, there's a significant difference. Thank you for listening.
Thank you, Indo. Please welcome Clancy McColl.
Imagine one material that does it all. A magnetopolymer matrix composite that combines electromagnetic performance with a mechanical load-bearing surface. The vision for this research incorporates the next generation unmanned air vehicles made from one advanced multifunctional material. In the past, aircraft were built using isolated components, and as you can see on the right here, we have a comparison of a Boeing 787 as a passenger liner and a defense-based platform. You can see extra sensors that have been put on the aircraft that degrade the aerodynamic performance and also increase the volume and weight of the structure. Our solution is a structurally integrated system that incorporates, which is a magnetopolymer matrix composite. What is a magnetopolymer matrix composite? It's a passively load-bearing surface or structure that incorporates one or many functions. The intent of this is to improve the functionality whilst reducing the volume and weight of the structure. On the right, you can see a sample of our composite that we've produced that has been taken an X-ray topography at the Australian synchrotron, showing the distribution of the ion loading in the composite structure. There's been quite a bit of a research gap in the relationship between the structural performance and the electromagnetic domain, and this is poorly addressed. Our future directions are incorporating streamlined manufacturing. Currently, our manufacturing is very inconsistent and very labour intensive. We also want to incorporate composite fibres to increase the structural performance of the composite. Also exploring the 3D additive manufacturing printing capabilities of this new material, and also explore the synergistic behaviours between the electromagnetic domain and the mechanical domain. I'd like to just thank you for listening and have a good day.
Thank you, Clancy. Please welcome James Ryan.
Hello, my name is James Ryan and I'm currently an undergraduate at Swinburne University. I've been working on what I'm calling damage-tolerant topology optimization. So topology optimization is an algorithm that automatically creates structures by choosing where to place material within a design region. For example, here we have a rectangular design region with a single point load. applied on the right side and a constraint on the left, and topology optimization automatically creates an optimal structure to solve the problem. Topology optimization is an industry standard algorithm that allows engineers to design optimal structures for a task. It allows engineers to create lighter parts with larger strength to weight ratios, which saves money on the cost of material, and it also creates lighter structures that are perfect for the light rate requirements of an aircraft. One issue with topology optimization is that the structures it produces are not robust to damage, as topology optimization does not take potential damage into account. Typically, damaging a single member of a topology optimized structure will cause it to fail. And in an application in the aerospace domain, you want to design a robust structure that is resistant to damage. If damage does occur, you don't want the structure to fail. You want a robust structure that stays intact so that it can last as long as possible. So I've been working on making topology optimization that takes damage into account. This version of the algorithm optimizes over multiple damaged versions of the structure at the same time, and it produces damage-tolerant structures as a result. So here is an example of a damage-tolerant structure produced by the algorithm compared to a structure produced by the regular algorithm. And as you can see on the left, when the regular structure has a small square section removed from it, the resulting deformation, although this is exaggerated, this is a times 100 scale, but even when it's just 1, it's quite noticeable in the simulation, quite a large deformation, whereas the damage-tolerant structure, you can remove the exact same square patch and it works just fine, and there's actually 8 different damage cases considered here in a 2x4 pattern. So my work has been primarily focused on creating the algorithm with open source tools so that it's free for DST to use and doesn't require commercial software licenses, which can be very expensive. And I've been aiming to replicate the results from a paper by Zhao and Fleury, who produced structures using the commercial software OptiStruct. And here you can see their structures on the right and my structures on the left, along with an animation of the optimization in action. I guess I'll have to go now. Thank you.
Thank you, James. Please welcome Meaghan Smith.
Hi, my name is Meaghan Smith. I'm a physics student from Swinburne University, and for the past year and a bit, I've been working with the Autonomous Aerial Systems Group, whose objective has been to... Is that working? There we go. Whose objective has been to design a drone that can navigate itself autonomously and carry out reconnaissance missions independently within an urban environment. Now, an urban environment is one that is full of lots of complex, dynamic obstacles. So in the context of defence, this would be something like an abandoned building that soldiers will need to enter, but could house several potentially deadly and unknown hazards. Basically lots of uncontrollable and unknown variables, and with the added difficulty of various signal interferences, so you have unreliable GPS. Now, with these drones to work and support these soldiers in the field, they could be actually sent in first to search for danger inside this building instead of a soldier. However, it is not only impractical but quite dangerous for a soldier to try and split their attention between manually piloting one of these drones and actually keeping themselves safe and aware in such an unknown environment. This emphasises the need for drone autonomy and independence, as it not only gives the soldiers more tools to get the job done, but it makes the job safer. Now, the first step to achieving drone autonomy without GPS is that we need to give it a sense of its surroundings. Essentially, we need to give it eyes. So my group experimented with this in the form of various sensors that could measure distances from solid objects, such as LiDAR and radar, and they were successful. So this is what would be sent back to the soldiers waiting outside that abandoned building, and gives them important information regarding room layout and potential blind spots. However, this presents a new problem. You see, LiDARs, much like our own eyes, are quite sensitive to airborne particles and can be negatively affected. So the advantage is that we have access to the brain that controls these sensors, and so we theorized that if we could characterize the sensor behavior with respect to increasing aerosol concentration, we could actually locate the point at which we would lose navigational capability and then give this information to the onboard computer, at which point it would then be able to detect when it's getting into trouble and get itself out of there. Now, I created a predictive model that showed that the aerosol particles would actually scatter the LiDAR signal. And so we theorized that this would show itself in terms of random noisy measurement returns from the sensor indicating accuracy loss. But this is not what we saw. Instead, we saw an artificial altitude drop, something that was completely indistinguishable from an actual altitude drop. We concluded that this was due to some unintuitive signal processing, and we found more information about what we needed to know.
Thank you, Meaghan. Please welcome Alex Blain.
Hi there. I'm Alexander Blain. I'm a student at Swinburne studying robotics and mechatronics engineering. And for the past year, I've been with the AAS group, specifically with the Urban Operations Program, focusing on enabling drones to operate in complex, congested, and contested environments. So, as Meaghan had previously stated, the ability to have drones operate in autonomously GPS-denied environments, including with visual obscurance such as smoke, is super important when you're trying to operate in a cluttered urban environment. Therefore, especially in the first half of the year, I spent a lot of my time assisting the Aerospace Composites group, working on a new radar-enabled vehicle dubbed Halo, with 4 outward and 1 downward-looking radars to achieve localization. And it's based on a design previously built in 2017. After selecting the powertrain for the vehicle, I worked quite closely with Salloum of the Aerospace Composites group in helping them as they designed all the embedded electronics, the modular motor attachments, and the main carbon fiber mainframe. And this is really important as it represents a departure from what we used to do, which is where we buy an off-the-shelf frame, and now we're actually trying to utilize DST's abilities with composites to actually get more of a custom, more of a bespoke design. So due to delays with Halo, I moved on to other things. So I created a simulation using ROS and the Gazebo simulation software. Essentially, it was like a high-level algorithm checker. So if we developed a new path planning algorithm, we could actually make sure it's not going to cause a drone to crash by testing it in the simulation first. Another area of active research is how do we get a drone to basically take off and then fly via a series of waypoints to the actual end goal. Currently what it does is something called train stopping. So it will take off, will yaw to the direction of the first waypoint, will fly straight to it and then stop, and then yaw to the next and then fly it straight to it and then stop. And this is really obviously not ideal. So this resulted in me expanding my previous simulation work and implementing a trajectory controller. And although I ran out of time to properly implement it, I realized how much this type of problem really interests me. And as such, I'll be working with DST this year as well for my final year project. So we can hopefully have drones not only operating autonomously, but efficiently as well. Thank you.
Thank you, Alex. Please now welcome Salloum.
Hi, my name's Jared. I was working with the Advanced Composites team in the Aerospace division last year through my IEP. Our goal was to improve efficiency of structures by integrating functionality into already existing structural components. More specifically, what our main deliverable is conformal antennas. With traditional antennas, they can often be bulky, unaerodynamic, like in the case of on a plane. They require structural reinforcement, which is extra work and extra weight, and they're susceptible to damage because they're a much bigger target. By introducing a conformal antenna which is embedded into a composite skin of a body, you eliminate a lot of these drawbacks. Another broad function that we deliver is just something like integrating wiring and electronics into the body or into a structural component of a body. So in that example on the right, that's what we made for the Halo project, which we've just spoken about. The way we do this is, one method would be to coat a carbon veil with copper and then etch away any regions where you don't want conductive material, and then you would carefully lay that onto a fiberglass piece. Or you can sew in copper into a fiberglass piece in the places where you do want the conductive material. And in both cases, you then have a fiberglass piece which you can lay up in the same manner that you would any other fiberglass piece. And it doesn't affect the cure cycles at all. So it's very easy to work with in that sense, and it conforms to whatever surface you put it on. So we developed a drone body last year, which had fiberglass pieces running through the center with sewn in copper circuitry. And if you look in the top row of pictures, there's a copper piece which, when you post cure and flip that over, those copper pieces look like what's on the bottom right, and you have an exposed copper pad which you can connect to. Through the middle, which is unseen after the cure, that copper pad protrudes into those fiberglass pieces and folds onto the circuitry so that you have a complete circuit running throughout the body of the drone. And you can directly connect your motor to the exposed copper on the arms, and then you can directly connect your battery into the exposed copper in the middle, so that you don't have wiring running through there that you have to manage to avoid other stuff. It's not likely to tangle, you don't have to tie stuff down, and it looks a lot neater. The next stage that we would be looking at is to put a shell over the drone, a composite shell, very thin and lightweight, and each surface of that shell would have a conformal antenna, and that would be used for navigation purposes through particle contaminants like smoke, which was just spoken about. So thank you.
Thank you, Jared. Please now welcome Liam Thomson.
Good afternoon, everyone. My name is Liam Thomson. I'm a nanotechnology undergraduate from La Trobe University, and I've been working in the Aerospace division at DST over the summer. Together, we've been developing energy storage solutions for aerial transport vehicles, such as UAVs and drones. These vehicles have complex power requirements as they need to maintain long flight times and high power loads. This is achieved using a hybrid energy source, which combines the long-duration energy supply of lithium-ion batteries and the high power supply of supercapacitors. Tailored towards high-power applications, the supercapacitors facilitate rapid flight, high-power communication, lasers, and camera flashes. They have a high power density and complement battery technology, which has high energy density. They are structural, as they are made from carbon fiber reinforced polymer, and they are resilient, lasting thousands of charge cycles at high power loads, while lithium ion can only last a few hundred. They are to be integrated into the body of vehicles, much like Volvo's project incorporating energy storage into their car panels. The supercapacitors will add little to no weight, take up little to no room, maintain comparable load-bearing ability, and will not ignite or expand when punctured. Arrays of supercapacitors are to be integrated into key areas of the vehicle under the lowest average load. These devices are constructed from load-bearing materials such as carbon fiber and carbon nanotubes, and they are separated by a piece of woven glass fiber. We have been improving the separator layer by depositing a thin film of boron nitride nanotubes onto its surface. This is to improve its insulating properties and prevent internal shorting. Here we can see individual boron nitride nanotubes on a toe of glass fiber and the films that we've been able to create. The main challenge in this work stems from the fact that boron nitride nanotubes are extremely inert and stable suspensions are challenging to achieve. While the deposition method is simple, the suspensions are very sensitive to contaminants. Majority of my work involves the creation and refinement of standard methods in creating stable suspensions and consistent thin films. Currently, we are testing the effect that the thin films have on the performance of the supercapacitors. In the future, we intend to scale up the production process to create large panels for the incorporation into large vehicles. But fundamentally, the supercapacitors are energy storage devices and are not simply limited to their use in vehicles. Thank you.
Thank you, Liam. Can I now have the AD presenters back to the front, please? Does anyone have any questions of the presenters?
What sort of parameters did you use for your particle swarm optimizer?
The particle swarm optimization. So I run 2 different particle swarm optimizations. One was successful, one we had a little bit more difficulty with. The first one with the difficulty was running over the impedance curve of the relaxoferroelectric elements. And I think it was, off the top of my head, something like 16 to 19, something like that, around independent material parameters. So what we did was use COMSOL FE modelling to try and iterate through material parameters to match the impedance curve from COMSOL with what we received in the lab, essentially hypothesising that all material parameters would eventually solve to what each individual crystal is, and we'd have 2 matching impedance curves. And that was unsuccessful just due to the amount of complication behind an impedance curve for these elements and also the amount of data points to get a good read. And the second one was in the material characterisation for piezoelectric charge coefficients, D31 and D32, I don't know if that is of any interest, but we could figure out what they were from experiment in the lab which we created, and we essentially just ran a formula which was the analytical solutions finding the piezoelectric charge coefficients which defined that voltage curve which we received in the lab. So it's a bit of a explanation for, if you're interested, I can chat to you about the setup. But essentially there was one with FE modelling and one with a formula-driven analytical approach. No worries. Sorry to everyone.
Any other last questions?
Hey, my question's for James regarding the topology and structure thing. So I'm not much of a modeler, but you were talking about how you could use, like you're trying to take sudden increases in impact or something into account on top of just the normal optimal structure, right? Couldn't you just normally take that into account by increasing the initial load on the developing structure? Like instead of just saying, say for example, the load is like 60 newtons or whatever, right, and you're like, oh, what about an increase in load? Can't you just put the initial load as 100, or is it much more complex than that?
Right, well, technically just increasing the load usually results in the same structure from the optimization, and also we're not optimizing for sudden impacts. We're optimizing for if a hypothetical region of material was removed from the structure for any reason whatsoever. And since topology optimization doesn't have any defined members before it actually creates the structure, instead of doing the damage as a member is removed or part of the or a particular part, we just take away regions of area, and that's what it's optimizing for if those regions were removed.
For Jared, who did the antennas, what is the risk of damage to these antennas compared to conventional antennas?
It's still susceptible to damage because it is underneath a composite material, but it's much less of a target is the main benefit there. So if it was something was going to strike the body, that's going to get damaged no matter what. But if something was to strike an external antenna, that can be avoided by having the antenna embedded in the skin.
Thank you.
I wasn't really the antenna specialist. I was the layup specialist, but not a question I can answer, sorry.
think that's all the questions. So thank you very much for presenting. The next presenters will be from the Research Services Division, or RSD. The two students are from the Scientific and Engineering Services, which is part of RSD. CES provides specialised scientific engineering, design and fabrication solutions. CES services include mechanical and electrical engineering, design, drafting and fabrication, microengineering and applied scientific imaging. Please welcome our first presenter, Luke Bartholomeuw.
Has your computer ever failed because it got too hot? Have you ever left your phone in the sun and came back to it not responding? Has your car ever overheated? Overheating is one of the biggest problems in technology, as it can cause parts to not work as effectively or even fail completely. So for decades, we've been designing heat exchangers like this, which move heat from one body to the cooling plate and then uses a cold fluid inside the pipe to take the heat away. In today's technology-driven society, we're striving to produce the most efficient heat transfer devices by maximising the surface area between the cooling plate and the cold fluid. But this requires complex shapes inside the pipe, and today's technology just isn't capable of this. But what if there's a new manufacturing method that allows you to have any interior shape? That's exactly what metal 3D printing gives you. We can rapidly produce products for a low cost, with minimal material waste and any level of complexity, so our dreams of huge surface areas are finally possible. This kind of capability gave me the chance to work with Defence's laser group to see if we can produce cooling plates with the performance of this, but with the size, weight, and cost of just this. So for the last 10 weeks, I've been working on this base design, putting different structures inside the pipe, like cones and lattices, and seeing how the performance changes. Lattices were the really exciting part of this project, as there's no way of making them without 3D printing, and their huge surface area to mass ratio make them ideal for heat exchangers. I took Defence's lattice library and filtered through them until I had two designs that had the best surface area to mass ratio, as well as being easy to 3D print. I then made my own models of these two, multiplied them to fill the cooling plate, and then added my base design. That's another huge benefit of lattices. The repeated structure make it easy to modify the surface area to increase heat transfer, but you can also use it to control energy losses by how much your lattice obstructs the fluid. For testing, the cooling plate was attached to a high-powered laser diode that was applied by the laser group. As the laser heats up, the blue cold water inlet extracts the heat and gradually gets hotter until it reaches the red exit. This temperature difference from blue to red is what determines how thermally effective the cooling plate is. So we searched for a design that had the hottest exit temperature. We found that the low to medium density lattices gave the best results, so further testing in this area must be done. The next steps in this project are to answer the following questions. With our data on the current internal structures, can we further optimize our performance? And is our serpentine design the most effective? Can we apply our structures to different bases and get even better results? Thank you.
Thank you, Luke. Please now welcome Marck Hubczenko.
Hello everyone. So I'm going to be talking a little bit about 3D printing using a robot arm. So standard 3D printing, the most standard form of 3D printing is FDM 3D printing, which stands for fused deposition modeling. And the way it works is you heat a filament in an extruder, and the extruder moves around depositing material layer by layer until you build your object. However, there are some limitations with standard FDM 3D printing. It's got a limited workspace for the size of the machine, and it's constrained to 3 axes of movement. And so that means all the layers are the same orientation. You often need supports to actually make parts, and you can only print onto a flat surface. So a robot arm could actually be used to overcome some of these. So a robot arm has access to 6 degrees of freedom, and so what that means is the extruder can be at lots of different angles, and you could potentially print on uneven surfaces or even change the orientation of the layers during the print. It also has a very large reach and workspace for the size of the machine. So how would we actually do this? Well, the standard workflow for 3D printing is you design your model in modeling software, Then you take that model and you put it into software called a slicer, which takes your model and cuts it into lots of layers and generates the toolpath for each layer. It then outputs this in the form of G-code, where G-code is a generic machine language that contains all your instructions like where to move and how fast. The G-code is then passed into a controller which reads it and generates all the electrical signals for the various motors and parts of the machine to produce your 3D print. So for a robot arm, we need to convert the G-code into something the robot arm controller could actually understand, such as we need a translator. So this is where my work has been involved at DST. So whilst at DST, I set up a translator which reads in G-code and then generates a toolpath that the robot arm could actually use. It then generates the joint angles necessary for all the movement, and then running a simulation allows me to go through the full movement as well as tracing the path. So on this slide you can see 6 states from start to finish of printing a boat using a robot arm. Also in my translator, it differentiates between traveling and extruding, and so this allows me to differentiate the type of movement. So traveling is fast but less accurate, whilst extruding is slower but more accurate. So some opportunities from this sort of thing is pick and place electronics directly into your part whilst it's printing. The varying extruder orientations could allow for some unique material properties or printing on uneven surfaces, and you could even attach the arm to a track, and that could further increase the workspace. And so future steps in this project involve making a physical 3D printer arm and improving the translator and the simulation. Thank you all for listening.
Thank you, Mark. Can I please have the RSD presenters back to the front? Does anyone have any questions?
I have a question for James. So on the fluid heat pipes.
Yep.
So it looked like you're using a homogeneous lattice. As the fluid transfers through the pipe, its temperature which will change, and then it'll change its viscosity. Did you explore using heterogeneous lattices that take advantage of that throughout the pipe? Because you could do that with your 3D printers.
No, we didn't. We just used one specific repeated cube and just multiplied that all the way through. Because you need connectors between the different cubes. So I feel like if you have different structures going into the next one, they might not connect. But you can really easily fix that by just having them all the same.
Thanks.
Just another question for Luke regarding the lattice. Is there any notable disadvantages to using a 3D printing method compared to conventional? Because with 3D printing of metals, is there any kind of change in properties that would lead to a reduced conductivity? Or even with fine lattice, it means that there's a certain level of coolant fluid that it can't reach a certain viscosity, or you can't pump it too quickly. Is there any notable disadvantages, or is it just the wonder, a new wonder technology?
It's almost the wonder technology. You can get densities of around above 99% of just a raw material, but your conductivity goes down about 10%. So that's the kind of trade-off that you have.
Another question for Luke. Just wondering, with your structures, were you doing different materials as well? Were you changing the actual metal filament that you were using, or was it purely a structural analysis?
We only used aluminium. The changeover for 3D printers between materials is a week. So when you have not too long to do it, you don't have enough time to change materials. Plus aluminium is the best conductivity one that we have. You can use copper, but you can't have a pure copper 3D print. Don't know why it doesn't want a 3D print, but it just does. So you have to have a mixture for aluminium copper to get that.
Another question for the cooling plate. I think the previous question just answered it though, but I was going to ask, have you tested this in the real world? Have you had any problems, or how does it go?
Yeah, so we tested it last week, I think, and with our high-powered laser diode, it kept it below the maximum temperature. So I think as soon as you get to 35 degrees, your diode starts failing, and we kept it to around 26, 27 degrees. So yeah, it worked pretty well.
So another question for Luke. So do you work like strictly with the small scale, or is there like a large diminishing returns?
So kind of as Mark spoke about, you have a really kind of strict size restriction on how big your plates can be. So I think the ones that we have are 50 centimeters by 50 centimeters by 50. So obviously if you want to go larger than that, you'd have to print multiple components. So that's where you have to go, but small 3D prints are pretty easy to make.
A question on the robot arm 3D printing, you know.
Yes.
I was just wondering what degree of fidelity your system is capable of compared to modern alternatives.
So in the simulation, it was mainly just trajectory, like taking your coordinates from your G code and then generating a trajectory. And so in my translator, I was able to kind of choose how accurate I wanted to be. And so when we actually make the physical one, we obviously have to do testing to see what fidelity it actually can do in the real world. So at the moment, I can't really say that it's this accurate. There's just like a choice, and we haven't actually done testing to see if that answers your question.
Back to the metal 3D printing. You mentioned the diodes were staying at about 27, 28 degrees. How does that compare with old systems?
I don't know how they actually performed, but I had one test that had nothing inside the plate, so close enough to what the old systems were. And that stayed at 27.7 degrees, where the best lattice was 26.1. So if you scale that up, put a higher powered laser diode in it, those differences get larger. So yeah, so it was actually giving us decent results.
Okay. Thank you to all the presenters this morning. It's now time to have a break. Please join us for lunch in the breakout space, and we'll meet back in this room at 1:30. Thank you.